Good afternoon, everyone. Welcome to today's webinar presented by 3D Systems Cimatron Software. I'm Cynthia Kustosh with Mold Making Technology. Today's topic is conformal cooling right for you? Successfully cooling a part in a mold can be a hit or miss kind of task. Many molded parts suffer due to warpage because of irregularities or imbalances in the cooling process. Some molders are finding that the cooling process is improved and the overall time required for cooling is greatly reduced by using conformal cooling. In this webinar, you will learn what is conformal cooling, how does it compare to traditional cooling processes, how is it accomplished, and what are the benefits. Today's presenter is David Lindeman. David is an applications engineer for 3D Systems Cimatron Software Business Unit. Prior to the 3D Systems acquisition, David worked for Cimatron for several years. In addition to his extensive CAD/CAM knowledge, he also has 15 years of experience in plastics engineering and injection mold design, as well as 6 years in metal forming and die design. David has been involved in the injection molding process from quotation to analyzing molding conditions and tool build, plus CNC programming. Now, as you listen to the presentation, please feel free to ask questions by typing them in the questions panel on your computer. David will answer them at the end of the presentation. As a reminder, this webinar is being recorded, so you will be able to listen to it online later. Thanks again for taking time to be with us today, and here's David.
Thank you very much, Cindy. Appreciate it. Of course, I work with Cimatron. I'm part of 3D Systems. I'm an application engineer. Perhaps you've heard some news about Cimatron that recently we've been acquired by 3D Systems and are now part of their family. As we look forward to all the technology that brings to light and that can be worked with together, we like to think we present a digital thread from design to manufacturing. And that includes all sorts of technologies, hardware, software, you name it, anything that can be involved in creating the part from conception to manufacturing to production. And for people involved in mold making and die making, that means we present an end-to-end CAD/CAM solution for making molds and dies. So I thank you for your attention. All your time is very important, so let's get on with our subject of conformal cooling. We're going to talk about what conformal cooling is, with some of the basic guidelines involved in successfully using conformal cooling. To do that, though, we have to understand the nature of the printing process. There's some key things to keep in mind when designing conformal cooling. We have a real-world example to show you, too, that we can learn an awful lot from. It's a great example. And then at the end of our discussion, we have that question, is it for you? We'll talk about some facts and figures, basically, associated with conformal cooling. What is conformal cooling? The simplest description is to say it's a cooling passageway which follows the shape or profile of the core. So in the example you see in the upper right, standard cooling, typically in mold making, cooling is handled by drilling lines, standard drill lines that intersect, and then baffles or bubblers are used to direct the water up and into those cooling lines. With conformal cooling, there you see the lower example, it's following a helical twisting pattern. And the idea is it's conforming to the shape of that core as it routes itself up, across, and then back down using that helical pattern. That's one example of a type of conformal cooling, very much driven by the geometry of the core. Well, the purpose behind conformal cooling is to rapidly and uniformly cool the part. There in the graphics you see a couple of examples, one of a standard cooling channel with a lot of heat left in the part and the deeper parts of the core versus conformal cooling where the option or the idea is to try to get all the heat out at once in a uniform measure. So there's a couple of important reasons why we do that. Having a uniform distance from the part, that means efficient cooling, which is going to result in a shorter cycle time. Like you look at those two diagrams, straight drilled lines like on the left-hand example versus the conformal lines following the shape. On the left, there's really only 3 spots you'd call sweet spots where we're actually efficiently getting the most out of that water line. Whereas on the other example, the whole line itself is right there in the sweet spot. The whole thing is working in order to get the heat out of the core. If I were to ask you which of these two would present an out of round condition, well, most likely, wouldn't you say that the standard drill line would present something where the part could become out of round because it's not following the shape of the part? So the idea is having more water actually working for you more efficiently and being able to avoid dead spots that could occur because of crossing drill lines like you see here. And one of the benefits could very well be that your water line may end up becoming shorter linearly. You think of a real big job like maybe a bumper fascia. We've got just row after row of bubblers or bafflers going into that core to try to cool it. Or perhaps on the cavity side, you use a gun drill application to shoot those water lines in and try to intersect them so that you start to follow the curvature of the bumper. There's a lot of distance involved in drilling and working with that. That brings us to the next other important point. If the water is affecting that out of round condition, then it certainly is going to affect the warpage, because if I can get the cooling to take the heat out uniformly, it's going to reduce the overall warpage, which is a big consideration when considering conformal cooling. There you see one of the many graphic pieces that are available to look at showing the different tests that have been done to show the reduction in warpage due to uniform cooling. So we've touched on the two biggest benefits of why people right now are looking at conformal cooling and why it's starting to take hold. The biggest thing is reducing the cooling time, which is going to reduce the overall cycle time. If that's the case, then that's reducing the piece part price. And who knows, maybe not using conformal cooling means I'm throwing money away when it comes to production. The other may be that the quality concerns associated with the part are such that the customer wants something like conformal cooling to have the assurance that their part is not going to have the warpage in it, or at least reduced warpage. So needless to say, there certainly are some challenges involved in conformal cooling designs. Because we're not doing just straight drill lines, we have to stop and think about how we're going to go about doing it. Having a constant offset from the core face is one of the most crucial features of this, because it's what's going to help us uniformly get the heat out. And often that means following a 3D trajectory like you see in that first example that we looked at before, the helical water line shooting up and across. Sometimes the way the geometry is, you just have to take what it gives you, like the second example that we say is so-so. It's basically jumping up and diving down as it tries to reach up into those cores, but it has to avoid some deep ribs along the way. And then sometimes it's just difficult because of the geometry. There's so much involved in terms of part geometry, trying to get into areas that may require a little bit of ingenuity on our part in order to get a nice cooling line into some areas. What's important though is we have some guidelines. Pretty much everywhere I've checked, the resources that I've looked at, the guidelines are pretty consistent from source to source. One is follow the shape. It makes sense to keep it uniform all the way around the part. You'll have uniform cooling. So here's an example of the water line following around that cavity. That applies to if the water line is going underneath it. So it's a fixed 3D offset that we're concerned with. All right? So there's a good example of keeping that uniform distance around our cavity or core face, whatever the case may be. We need to be concerned with equal distribution of the centers of our water line. It's easy to think about these as being like planar. That's kind of what we're used to because that's how we would set up our drilling. Let's try to cut it into planar applications so all the drill lines intersect. Looking at that diagram, you see the shadowy gray is the true 3D offset. That's the true distance off that part. So we'd want the water line to follow that and stay glued to that. And the arrows kind of show you how by that shift we need equal distribution, which means that the water line is going to drift in a bit. We're not so concerned about keeping everything planar. What's important is keeping the distance between things around the surfaces of the part geometry. This is something that's very important. We need to have a fixed section area that goes through the water line. So I'm thinking about a round hole that's going to have a cross section. that cross-section has an area. That area is what we need to keep constant throughout the length of the water line, as much as we possibly can. Now there's going to be areas where we may want to squeeze that water line between a couple of mold features. In doing that, though, we still want to have the same fixed offset as much as possible too, and that's a very important thing. So if we're squeezing that water line, then we may change the shape a bit, narrow it. If we narrow it, we also need to elongate it like this diagram shows so that cross-sectional area stays the same. That way we're getting the same water flow going through the whole water line. If it starts to reduce, that's going to slow down our water flow. And the next guideline is also important. We're saying no large overhanging faces. What is an overhanging face? And why does that square with the X mean I can't use it? It's not a good example to use versus the other two with the green check. Why are those good examples of water lines? When you think about the process of printing the core, try to get my mouse to move here. Basically, we're layering layer and layer down upon one another as we build up the steel on both sides of that water line. Well, what sits in between here is just powder. So as we get to the top, all we have to support the top when we lay that last layer across that closes the top of the water line is powder, and that's not enough. We're trying to stretch this all the way across with no support. Okay, so that's what we call an overhanging face. It's sticking out over a void with nothing but powder in it. What's there to support it? All right, that's an important thing to realize about the printing process. Now you can compare that with turning it 45 degrees, where you see this angled wall, or putting a crown on it like this. Now as we layer across it, there's a little bit of an overhang there that it can grab a hold of for the next layer. And now we can successfully layer it up and keep the geometry of the water line as we've designed it. That's a real important thing to keep in mind, and it can vary from printer to printer depending upon what you have. So you have to know that about your printer. Obviously, you need a legal water path. Like the top example, the water could shoot in there from the left, and then maybe it'll want to meander downward because it's shorter distance and totally ignore the top, right? We have to have a legal water path where we know water is going to flow uniformly all the way through the water line. Best way to do that is to ensure that is to have one entry, one exit, and no diverging paths off of it like the bottom example illustrates. And finally, we're throwing in there analysis as part of our guidelines. If we go through the work of developing these water lines and following these rules, we want to make sure that it's doing what we would anticipate it to do. Using an analysis software such as Moldex that helps us to see that we're getting all the heat out uniformly, we're not leaving hot spots. That's a big part of knowing that our design is successful for what we want to accomplish. Those guidelines will come up again and again as we go through the presentation, and make sure that we point those out. Let's look at a case study here. One of our engineers worked on this with a customer. You can see, looking at that core, it's got some thick areas, some thin areas. It's also got some very deep ribs that we have to avoid and kind of work our way around. And the resulting water line is shown there on the right. So there's a couple of techniques employed in building this. It's not just one automatic thing, not at all. There's some reasoning behind the things that you're looking at in that picture. We'll go through that. But it gives you an idea of how far you can go with conformal cooling and what it can really do for you. We'll go right to the proof in the pudding here. The resulting the results that we got from using conformal cooling versus the standard cooling techniques are shown here. Basically, it reduced the cooling time of the cycle from 82 seconds to 62 seconds, which is pretty significant in terms of your overall machine time or piece part price. So if your production volume says you need to reduce your time to save money, this is a good example of why conformal cooling would be a good choice. But also the quality of the part, the warpage has been reduced by 20%. There in the diagram, you can see how the conformal cooling on the left is in a nice green and blue, showing that the heat has been uniformly drawn out of the core. Whereas on the right, you can see there's some heat trapped on the very tip still. That's definitely going to affect the part. It's going to affect the warpage of that part. And as we go through this too, you'll see how, again, we had to keep constant offset from the faces. That's crucial. We have to keep to a 3D trajectory to keep wrapped along the shape and contour of the geometry of the core. And you can't use the same cross-section of the waterline. For it to fit into certain areas, there are times it has to change its shape, sometimes quite dramatically. And there again, you see the rule is trying to be applied here, where we're going to try to keep that cross-sectional area through the waterline the same no matter what the shape is. And if we do have to have a horizontal top of any kind, we want to reduce that to as small as possible so that we don't have the problem of overhanging faces. All right, so let's go take a look at the part here. Hopefully you can see that on my screen now as I'm rotating it around. Again, you see the very deep ribs that result in this very narrow coring area that you should see flashing on your screen right now. And it gets into some beefier areas back behind it. So there's quite a bit going on this little core. As we take a drag section through the part itself, let's look at what we see with those water lines. And hopefully I'll be able to time it where I can catch a cross section for you. There's one developing. Yep, just passed it. Right here. There. All right. You see how that water line is moving across the core, getting into a different area, but the distance away from the outside is uniform. Also, you notice here in the corners, the round piping water line is also that distance from the outer edge. As we continue to drag this through, you should see other different shapes appear. Again, the idea is to keep it as equal distant from the outer edge as possible. And there you see it down into the tip, how it's had to completely change its shape. Looking at the cross-section here, there is no way that's the same area as in other places of this water line. Just to point that out to you, and we'll talk about that as we look a little closer at it. Let's look at this from another point of view here. And we'll turn off these outer faces for now. What you're looking at are two different water circuits, one in purple, one in blue. Looking at the blue one, you can see it's entering with the dark blue, it's meandering around, converging down here at the bottom, and then exiting out through the center. Along the way, it's changing shape. You might call this like a pipe type of water line, the way it's going around a 3D curve, the way it's working its way on a 3D trajectory. But right here, in order to get between a couple of different mold features, it had to be narrowed. Well, when narrowing it, we also elongated it. The idea again is keeping that constant cross-section. Along the way too, you see these transitions. Now, it's nice to keep it, nice and smooth, tangent to tangent transition if possible. The most important thing about this isn't so much perfect tangency, but that we're avoiding sharp corners. We don't want to have sharp corners anywhere because we want to avoid cracking in the core. So that's an interesting looking path, isn't it? A little bit involved in creating that. But it's also, the curvature shows how it's staying conformal to the shape of the coring. Now looking at the purple one, a whole lot more going on here. You have a pipe type of water line coming up here to the tip. There you see it now is following the shape of the core, and because that core is narrowed, this area had to be built by offsetting the core faces, intersecting them, constructing them, and then putting rounds on it so that we don't have any sharp edges. Then of course it had to be built so it could wrap over the top, come back down, and then it's set up again to go into the next core, and here we're getting into that super narrow area. All right. What that means is that the water flow is going to slow down here. There's just no getting around that. It's going to slow in those areas, meaning it's going to slow in the overall time it takes the water to get up, all the way around, and then back down through the exit down here in the center. It's going to run slower than this water line. All right. Understanding that helps us to see that probably we're going to have to push that water in at a quicker rate in the purple rather than the blue. The idea of uniform, again, we want to get the heat out all at the same time. So that's a factor to consider when we start to see slowdowns or the distance in the total linear distance of the water line being different from circuit to circuit. Okay, and again, note the transitions, trying to avoid sharp corners. Note that there's a radius wherever possible. 1 millimeter radius is generally considered the minimum in order to have a water line where you don't have to worry about cracking. Okay. So you saw some examples there. Again, the constant offset from the face, 3D trajectory, understanding printer limitations, no hanging geometry. You see some more examples there at the red axis of a cross section that would create what we're calling hanging geometry, or where the top face of the water line is not supported by anything but just powder underneath it. And again, the new rule we've got to keep in mind, we talked about 1 millimeter minimum radius on everything wherever possible, along with that constant section area. Well, to do this, to build a water line like this, with all the attributes of the conformal cooling, means we need to have a CAD system that's got the tools that we need. We need to have a good modeler, something that can work with offset faces, something that can really help us to take advantage of solids, things like that. A dedicated analysis function, such as Moldex, where we can interrogate the water line, test the water line to see if it's getting the heat out of the core like we want it to. And maybe it means building the water line, checking it, looking at the results, tweaking it, checking it again. Certainly want to get the most out of the water line so that we have the best effect. And as far as your CAD system goes, it'd be nice to have some dedicated design functions specific to what we're trying to build here. Like, we know we're going to pipe along 3D trajectories. The shape of that pipe may be round, it may be something else. We need to be able to merge that with offset faces. So it's a CAD system that's got some robustness. Is something that's going to be necessary in order to develop a good conformal cooling line. So here's the result. Now you can actually see it brought to life. We printed this core both in metal and in plastic. I want you to pay attention to the overall sizes as we look at this, so that you can understand, just about how big this core was. Also, the upper right, you see that example printed. It's still sitting on the mounting block. All right, that's something we'll need to talk about too when it comes to prepping the core for what it needs to do. We went ahead and doubled the scale and just printed the water line so you could see it. It's an intriguing looking shape, isn't it? And also clear plastic with the core double size so that you can look into it and actually see the water circuit inside of the core. All right, so this part's about, 95 millimeter. You're looking, a little over 3.5 inches, something like that. 4.5, 5 inches tall, something like that. So it gives you a scope of the size of this part. Again, I want you to put that in your brain so you can remember that as we talk about this some more. Okay. Let's talk about printers and information regarding printers. Every printer is going to be a little different. So if you have a printer, you need to know your printer. Typically, the layering that's being built up of material as the part's printing will be somewhere between 0.02 millimeter to 0.05 millimeter, again depending upon your printer and what it's capable of doing. You can get a good round pipe in your printer depending upon what is the maximum allowable size. The older printers are going to let you get a round pipe something like 2 millimeters. It's about 80 thousandths, which isn't too awful big. Okay, and again, that's because the top of that round pipe or that water line could be unsupported. It will go across a 2 millimeter space with an unsupported round pipe and successfully be able to print it. Now, the newer printers give you quite a bit more to work with, as they can accommodate in some cases up to 8 millimeter, which is a decent size water line if we're piping our way through it. Also, there's something to consider when we're talking about that negative draft angle. That's that again associated with the overhanging face, what's hanging out over the waterline unsupported. Most of the older printers are going to want you to do it at about 45 degrees, that 45 degrees walls on top of your waterline, all right, that it can support. However, newer printers can let you reduce that angle down to 20 degrees, which is pretty nice. That's nearly getting toward flat. All right, so the newer printers are offering more and more flexibility when it comes to geometric design of the water lines. There's some things to know about the accuracy of your printer. Again, going to depend on your printer. We're seeing near the center of the printer things are more accurate. 0.05 millimeter of variance. As it starts to grow outward, the accuracy begins to diminish. All right, and as you can see the numbers as it gets further from the center of the printer. So that tells me I want to put my printed object right in the center as much as possible, right, when I'm building it up. Surface roughness. Now, instead of trying to put numbers to this, just understand what our roughness is coming from. Obviously, the roughness depends upon the size of the layer. As we build up those layers, we're going to get that overlapping. You're going to see the layers, basically, especially along the vertical walls. If you think about a tilted or an angled, sloping face, as it layers up, you'll see the layers kind of like stair steps. You might think of what you see when you run an NC roughing routine, how you see those stair steps. Nothing quite that dramatic is what's left behind by a cutter, but still you will see what the layering effect does as it builds up on those slopes. Now on the inside of the part, especially when it comes to the water lines, we're really not too concerned with roughness. In fact, it's something desirable because it creates turbulence in those areas in that water line, and that actually aids in helping to get the heat out of it. It raises a good question though. What is the best cross-sectional shape to use? If we can make any shape we want, what's the best one to use for conformal cooling? Well, again, you got to stick to the rules. It has to be printable, all right, per your printer. You do not want to put a support in the middle of your water line. It kind of defeats the purpose, so it has to have the size that the printer will support. Okay, and you have to, again, keep in mind the rules of the overhanging face. And we've talked about the simple shapes that you see there on the lower left, the round, the ellipse, those kind of shapes. The funny thing is, though, that they're finding that the circle is actually the least efficient when it comes to getting the heat out. That's because it has the most minimal amount of surface area to it. Some are using some, or they're doing some interesting things like you see on the right here, where they're using some unusual shapes. Like look at that star shape. You can think of it again with a 1 millimeter radius on all those corners. That's important. They could use this and keep that overhang as small as possible while they're building this. But what that gives them is more surface area and an unusual shape that can kind of shake the water up a bit, give it a little more turbulence. Or you remember the slide I showed you with the square, and I said that's not a good shape because it has that overhanging top? Well, what some are doing is taking that shape, driving it along a helical path, all right, so it looks like a spring winding its way up and then winding its way down, and then moving it at a spiral, driving it spirally along that helical path, so it's twisting as it goes. And this creates turbulence. It moves that flat off to the side, so it's only flat in certain areas, and they're finding that this is becoming a much more efficient water line because just of the shape, the geometry of the shape they're driving around that helical. So it's an interesting study, isn't it, when we think about what's being done right there, or right now in the industry. So now we've gone ahead and we've printed up our part. We've got our core. First thing we're going to have to do is remove it from the mounting plate. And you saw the example of the one that was printed. All right, and you saw that we're going to have to clean that up, cut that off. If there was any external supports holding our geometry together as we printed it, maybe there was something that was detached that would later be attached as the layering worked its way over to it, we'd have to remove those supports. We're not going to see that typically when it comes to a mold core, all right, but a lot of other times it's considered an important part of finishing a part after it's been printed. But we are going to have to finish the part all the way around with a finish milling operation. You know, of course, not worrying about the cooling lines, those are pretty much done. But the roughness, the outside surfaces of that core, we're going to have to finish mill those like we would something that had been pre-roughed. That means you're going to have to leave material on the outside of your core in order to have it there for the post-printing operations. Kind of like what this diagram is trying to show you. So thinking about what we said about your CAD system, you have to be able to offset the faces inside that uniform distance so that you can build your conformal waterline in those hard to reach areas. But also all over the part, we're going to have to offset those core faces to the outside so that we can have the minimum material that we need in order to finish mill it once we're done. So we're sending that model right to the printer with the offset. Now, if you just took it to a CNC mill and we're going to rough it, you could take your finished core geometry, say, let's leave 20 thousandths, 15 thousandths, and the cutter won't go in there. You know, maybe we've been a little spoiled by that. That's a nice feature to have. When it comes to this, though, we're sending a 3D model to the printer. That geometry has to be on that 3D model. It's not like something that we can have the machine fake it for us. Okay. So doing a comparison, okay, of a printed core versus a standard core. If we print it, we don't have to prepare the block. We don't have to square it up. Right? We don't have to do those typical things. We don't have to rough it or go through our semi-roughs and corner picks or semi-finishes. We can go right past all that. Probably not going to do a whole lot of drilling. We may have opted to drill the entry and exits of the water line, but the water line's going to be in there. That's the whole purpose for this anyway, right? But after that, things are the same. Okay, we're going to send the printed part out to be heat treated, just as we would anything that we've cut with standard NC. When it comes back, we're going to have to finish mill it, get it down to size. If there are long ribs, like the example we showed you, we're going to have to build an electrode, and we're going to have to finish those rib areas with the electrode. We're going to have to polish it, just like you would any other core. Okay. After we've gone through the comparison, the printing method still remains more expensive. Of course, it varies from job to job, but it is going to be more expensive. It's going to cost you more per core to print it. All right, so again, you weigh that versus down the road during the production when the part comes off the press quicker. Are you saving money there that would justify adding more money to the tooling here? Okay. I'm not sure I called this slide the right term or not, investment, but it's basically about you're thinking about this whole process now. You got a little bit of a flavor for what's involved in conformal cooling. Already you know it's going to involve some investment of equipment and time. Is it right for every job? Well, a lot of jobs you do, it may not be worth it in that you're making it just fine now the way it is. For the production volumes are such that you're not going to see down at the end, a return of that money. And it may be that the quality is something that's not so big a concern. However, if the part does have major quality concerns involving warpage, or if there is a significant reduction of the overall cooling time such that it does reduce the overall cycle on a big production run, you may be throwing money away by not doing it. So it's a decision to be made based upon the job or upon what the customer dictates is necessary for the quality of the part. When do we start using it? Well, it's no secret there are a lot of people out there who are doing conformal cooling. They're very successful at it. Okay, you used to have to go to YouTube and you can find all kinds of great movies that people put up there. They're very proud and happy with what they've done using conformal cooling. There's a lot of tech articles that you can read on the internet now that tell you how it's becoming more and more mainstream. You might think of it like when high-speed machining came out. At first, you had some that got on board with it. They thought it was extremely fascinating and cool. They jumped into it. They learned it. They kind of got going with it. Others of us, we sat back, we tried to gain more information. We understood it's not just a high-speed machine, right? You had to have the right tooling, you had to have the right setups, you know. But eventually there came a point where in the discussion, high speed became the normal. It became the standard. And the rest of us at that point might have been sitting there thinking, wait a minute, we're now a little behind the industry. We have to catch up because there are a lot more people doing high speed, or it's become the normal, much more than we thought it would be. And it appears that conformal cooling, 3D printing, is going to go that same route, is well on its way, in fact. Like I said, there's several examples of people who are successfully doing it. One that I did some research on made the claim that 30% of what they're doing involves conformal cooling, which is a significant part of their business. So if that's the one that's talking about it, you wonder if there are more that are actually doing quite a bit more with conformal cooling and just haven't said anything yet. Does that mean now we run out and buy a 3D printer? Well, if you do buy a 3D printer, you obviously want to get the right 3D printer. You want to have one that's going to support this kind of work with printing metals, right? So you can't just get a cheap one. You know, obviously some of these machines, some of these printers, they're high tech, they're going to cost a little bit of money. You might think though about, in a business sense, about how much money you might have been planning to spend on some CNC equipment over the next year or two. Typically we have to upgrade our CNC equipment, and as we do, we think about things like, oh, I want something now that's got a more rigid head, I want multi-axis control, I want to get something that's got high-speed capabilities. And while the prices of CNC equipment are competitive, still that starts to add up after a while. It might be easier for us to spend money on a CNC machine because we're figuring, well, I already know the work I'm going to put in it, and I can fill it. Whereas because we're not used to thinking about conformal cooling, we're uncertain as to what jobs are going to go into a 3D printer. So it's something to investigate, and it's something to think about in terms of how we're investing the years to come, in our business. And we have to figure in the time it takes to print something. All right, that example I showed you, remember what it was, right? 3.5, 5 inches. It took 100 hours to print that little core. So your printers are going to be busy printing cores if you go this route to achieve conformal cooling. Some have given some thought to this, and it's a very prudent way of looking at this. Makes a lot of sense. Decide to break into this process on a job-by-job basis. They've quoted a job. It's a perfect candidate for conformal cooling, but they're leery about investing in the equipment right now. They're uncertain about their own expertise at it. There are definitely some services that are available. A good one is Quick Parts. You can consult with them, look them up on the internet. Generally, we're saying it's low risk because all you're doing is providing a 3D model, and they're providing you a printed part. So as far as risk goes, it's associated just to that specific job. And it's a good way to break in to see if you're adjusting to the ideas of conformal cooling, if that's something that's going to really work. Again, we're seeing it move in the industry, and it's becoming more and more of a mainstream topic. When talking about what we need, though, we can't ignore software. All right. It's one thing to have a software provider. It's another thing to have a software provider that can help you. All right. Being part of 3D Systems, it's a big advantage because our software goes in hand with the printers and everything else. So it's do you have a provider that's just dumping software on you, or is it one that's helping you because it knows your business of mold making? Is the software itself capable of doing the type of geometry that we looked at, or is it just going to kind of get in the way, make it difficult? Does it have things that are dedicated to building conformal cooling lines, being able to check the geometry, and also being able to check the validity of the water circuit to make sure that you have a viable water line? And I think about what it would take on your own shop too. We're talking about training people, to think in terms of conformal cooling and giving them time so that they can develop their skill set, so that they're understanding and working comfortably with it. That example, again, just to fully disclose to you, the designer who worked in that, he's an engineer that we work with here, he says it took 3 days to design that water line that you see on the screen there. Now, bear in mind, that's more than just offsetting faces and doing all the CAD work. That's taking the water line, taking it through an analysis software like Moldex, check to make sure that the water line is going to take the heat out, there's no hot spots. If there's something that doesn't look right, it's going back, tweaking it, adjusting it, going back through the analysis again. So it's more of a process of 3 days rather than just sitting there actually building geometry for 3 days. And that's why that analysis tool is so important, so that we can double check the water line, make sure we're getting the most bang for our buck when it comes to the design time and effort that we're putting into making a good conformal cooling water line. So there's some food for thought about all this. It's definitely an interesting subject. It's one that's definitely taking off in the marketplace. Hopefully we've given you some things to think about. It's well worth your time to continue to investigate conformal cooling if it's something that's interesting to you. Again, with being part of 3D Systems and being part of Cimatron, we hope that we can offer services that will help develop 3D cooling lines like this and other mold-related things that we're assisting our customers with. So here's our contact information if you want to check us out. Dig a little deeper into what Cimatron and 3D Systems are all about and what services and things that they offer to you that might be exactly what you need for conformal cooling. And with that, I thank you very much for your time and attention. I appreciate your time is valuable, and I appreciate that you've chosen to spend it here this afternoon talking about conformal cooling. So if you have any questions, feel free to ask them. I'm not going to say I'm the expert, but I'll answer any question I can. Perhaps we'll find that even some of you may know quite a bit about conformal cooling as well, if you're interested in any sort of follow-up. With that, I'll give our attention back to Cindy, our moderator, and she can handle our question and answer session.
Thanks, Dave. We do have a few questions here for you. Pardon me. The first is, and you did address this with your case study, I believe, but I know some people might have come on online for the presentation later, so we'll ask it. Is following the part shape as critical if you have varying wall thicknesses in the part?
It is still critical, and that's because of the uniformity of taking the heat out of the core as much as it is the part. All right, so I'd say in your list of guidelines, maintaining that distance from the wall outside of the core is probably one of the most critical features, even more so than the cross section. At least that's from what I have learned, working with this engineer who did our case study for us.
Okay, next question. Is it your contention that conformal cooling is able to reduce warpage when the root cause is something like a glass-filled material, off-center gating, or some other root cause that is not related to cooling?
The root cause for those problems are still going to be there. I mean, that's part of design, right? What we're talking about is how the cooling will affect the warpage. If I don't get the heat out of the part uniformly, some areas are going to solidify before others. That's just, how the cooling operation works. So if there's an offset gate causing a problem, that offset gate will still cause a problem. I mean, that's just the geometry or the basic nature of the material we're working with.
Okay. The next question is, any guidelines for minimizing flow channel dimensions to prevent mineral deposits from impeding flow?
That I can't give you an intelligent answer on. I would have to say, to get that answer, I'd have to talk to people who are doing it, check some of my customers who are doing it, and see how they're handling mineral deposits. So, yeah, I can see where it's an issue. You get some real tight areas. So
maybe this gentleman can send you a private email and discuss it with you.
Yeah, let us do a little more research on that and see if we can get you an answer.
Okay. Next question. What is the recommended minimal distance from the water channel to the face of the part?
That's a good question. It's going to vary from job to job. Other than going through and measuring some of the examples I have, I can't give you a rule or guideline on that. So a lot of it's going to have to be basically upon the experience of what you can do. I mean, we always use rules of trying to have water lines avoid other things by 1/8 of an inch, 1/4 of an inch. It depended on the job, it depended on the customer. There are certain things like that that you factor in as far as how far you want to keep that water line away. Is there a safe distance? Sure. Is there a distance that's too far away? Sure. But honestly, I can't give you a rule on what's the best way to do that.
Okay. Next question. When the printed core is hardened, what hardness is achieved?
Okay. The answer I'll give you is based upon things I've researched myself. Okay. Things I've found out there looking up this subject. So you hear a disclaimer like, they're claiming, okay. What I found is information that says that the hardness that is achievable is 50 Rockwell, and that's using, a 6-hour process at 900 degrees to get that hardness. So the study that was done was comparing the core to a typical P20 core. Okay. Now when it comes to other materials, I haven't seen where a specific hardness that's achievable, but if it's comparable, I gotta think that it depends on the material you're printing, right? So I gotta think it's going to be comparable when it comes to hardness. At least that's the first study I've seen with the P20 example.
Okay, another question. How long does it take to finish an insert, and do most people order multiple inserts to avoid production shutdowns?
That's a very practical way to do it, is to have spares. How long does it take to finish an insert? It's going to depend upon the insert, how much time you're spending polishing and what type of polish you want on it, what type of finish. Depends upon how much time it takes on the NC machine to finish mill it. So that's going to be a hard one to answer because it's going to be a job by job. I can tell you, like the example, you see that it takes a bit longer to print, because it took 100 hours for that one example. Whereas after that, it's just a finish operation and polishing, right? So again, I can't give you a specific example. I think overall the time it takes to build a core is going to be longer with the printed method rather than the CNC method.
Okay. Next question. It's actually a two-parter, maybe a three-parter here. Let's see. What materials can you print? Can you print different materials in the same core? And what finishes can you achieve?
You can print all kinds of different materials. I know you can print stainless steel, tool steel. It is feasible to print different materials in the same component. As far as the polishing, you mean the finishing, they say that the printed method, again, this goes off on my own little research here, they're claiming that printing gives you 99.9% density. So whatever porosity is there is considered microscopic, and they're claiming they can get a B2 finish by polishing, which typically would be good enough. If you're looking at something that requires something better than that, like maybe an A2 finish for lens, then it becomes a factor you have to consider. As far as practicality, I'm not sure. I haven't dealt with anyone yet who is printing different materials in the same core, although it certainly is intriguing to think about, isn't it? Yeah.
Next question. Can you comment on the need for filtered cooling water?
I don't have experience with filtering it. I can see where it makes sense to avoid any kind of buildup. Is it more beneficial than not filtering it? I don't know. I gotta imagine it's going to be, again, the preference of the molding shop and their standards and how they do it, because the water line is the water line. It's just making sure that everything stays clean inside. So honestly, I can't say which is preferred, which isn't.
Okay. Next question. Is there a preference in analysis software for analyzing conformal cooling?
Our experience has been with Moldex, so that's what I would comment on. To fully disclose, we have a relationship with Moldex where they work with Cimatron to do these analysis. So basically, that's the one I would recommend. I know there's others out there, but I don't know a comparison between Moldex and the others because I've worked exclusively with Moldex.
All right. What about the durability of printed cores and cavities? What sort of shot life can you expect? And
That's
can
good.
you, okay, go ahead, answer that, and then I'll give you the other part.
Okay, that's a good question. I've seen a couple different claims now that say that it is the same as a machined core, and they're expecting 1 million shots per cavity is the general claim. Okay, so that's what we go with. They say it's the same. So I'm sorry, what's the rest of
Okay.
that question?
The rest of the question is, can you weld and repair printed cores and cavities, or do you need to print new ones when damage or wear occurs?
The information I've read is that you can, after printing, you can machine it, you can weld it, you can burn it, you can polish it, you can coat it. So pretty much you can do anything with it, typical to what you would any other core. So the answer I'll give you is yes, based upon the claims that I've read so far.
That's pretty good. Okay, next question. How do you clean these cooling circuits?
Yeah, again, that kind of goes back to those other questions. You have to flush them out. I don't know if some are using filtered water to try to avoid that. Others, obviously they're putting something into it to try to clean it. So it's the same way you clean, I guess, any other water circuit as best you can. It's good. I would think it's going to take pressure, push it up and out of there, but it's not like you could just unscrew the nozzle on the end and blow the water line out one line, all the way through the mold. It's going to be a little more complicated, but typically that's the only answer I can give you.
All right, you may have already answered this, but I'm going to ask it anyway. What material hardnesses are available in the printed steels?
Yeah, the 50 Rockwell is the one thing I have read. Okay, and that, again, that's comparable to P20. I imagine do some more research and we can find out, like what's possible with A2, S7, all those. Right now, the rule of thumb I'm hearing is that it's comparable to what you're used to working with or what's capable.
Okay, this next gentleman asks, what type of steel materials can be used to print inserts, and can you polish to A2 surface finish if required?
Yeah, we kind of answered that a bit about like the polishing. I know we can get a B2 finish. I haven't seen anyone say that, as right now they're saying A2 is, if it's critical like for A2, then perhaps not. You'd have to consider that. And then, the materials, the steels you can print with, I'm being told you can print with whatever steel you can get a hold of, so up to stainless steel. So I haven't had experience in working with any other type of material other than what you've seen here. So.
Okay. Can the printed steel be shut off on from the cavity half of the mold without cracking over time?
Yes, because it'll be hardened the same. So all the rules are the same as far as, the right type of geometry for shutoffs. Okay.
All righty. What is the minimal wall thickness of the steel walls where the cooling channel does a 180 turn?
I don't know. I'll just flat out say I do not know. That's a good question.
Something to follow up with.
Yeah, that is, you saw one example in there where it did come back up and down, but I don't know that there was a specific rule for that.
Okay. What type of metal is suggested for 3DP tools, 316?
3DP Tools 316.
I
I can't, yeah, that's going to be beyond my scope to be able to recommend a metal at this point.
Okay. Is there a benefit to using conformal cooling if you are molding long, flat parts?
Well, that's an interesting question. If it's long and flat and basically it runs the length of the part and stays straight, that might be a case where you wouldn't see as much because you can do so much, with a straight drill line for a long, flat, straight part. So it could be. The best way to find out would be just to design it, and then you can check it in the analysis software to see if it actually is saving you any time or not. So that'd be an interesting experiment to try to do. I can't say that anything just jumps out at me immediately. It would make you say, oh yeah, definitely. But hesitantly, I would say maybe in that case, that would be a candidate that wouldn't be the best for conformal cooling.
Alrighty, next question. What about fouling? With small water lines like this, fouling could restrict flow very fast.
Mm-hmm. It sure could. That's where you try to have as big a water line as you can. And in some cases, that is an issue. Like I said, you try to keep that constant cross-section so that you keep the flow going the same. If it's not there, then it does slow down the water line. Small water lines, that's going to be more of a challenge. So geometry at that point is geometry,
Right. Okay. This gentleman says, sorry, but I didn't follow what is meant by, quote, negative draft angle 45 degrees typical, newer printers up to 20 degrees when discussing printing information.
Gotcha.
Excellent presentation, by the way, he noted.
Oh. Well, what we're talking about is like a flat top to a water line. And the reason being, again, is because as you're building up the material along the sides of the water line, you're creating that channel, that void where the water line sits, and all that's inside of that at that point is powder. And the powder will not support that last line of print that goes across to close the top of the water line. All right, so that's what you call an overhanging face because it's hanging out over the void with nothing underneath it to support it. So the angle, or that negative draft that we're talking about, is where we're building the material up at a 45 degree along there so that each layer hangs out just a little bit more than the previous layer until it comes together at the top to form the water line. That's the negative draft angle that they're what they're calling a negative draft angle on the top of the water line. So you look at it that way, basically it's a solution to avoiding the overhanging face. I hope that answers the question.
Okay. So is the heat treat process different from printing steel than that of machines, from printed steel than that of machined steel?
Not that I'm aware of. The example I have, again, is that Rockwell of 50, 6 hours at 900 plus degrees, and that's how they heat treat it.
Okay. Is there an issue with porosity due to the printing process, or what sort of polished finish can we get? You already kind of addressed that about the polished finish, but about the porosity.
The number I found on that was that it's 99.9% dense. So the porosity, as they describe it, is microscopic. All right, so that's where they're achieving a B2 finish again.
Okay. Is Cimatron useful only for creating conformal cooling, or do you do other mold-related functions?
We do other mold-related things. We have complete set of tools for mold design, which includes all your standard components in the industry and catalog, or the ability to create your own mold sets, as you will. You also have standard water lines. You've got runner lines, ejector systems, ability to place ejector pins, all that. So it's what you'd call a full design package, as well as splitting and looking at the slides and lifters associated with the part.
Okay. We have time for one more question, and I thought this was a good one to end this wonderful webinar. How many shops are using Cimatron currently for mold making, mold design? And this one gentleman would like to know if you have a list of those shops.
Oh, a bunch, I know. Hundreds, thousands, I believe, worldwide. I would have to consult with I guess someone in management to release the information of the shop names. It'll be on my scope, but that'd be a good one to follow up on so we could understand You know, because not all mold shops are the same, but if it's, we could probably isolate the type of mold shops that would be akin to the work that he's doing. You know, it's like it's different doing a fascia molded Windsor than it is doing like an electrical component part somewhere else, you know, that kind of thing, because the molds are a bit different. So I could rest assured that many, many, many shops of different disciplines are using Cimatron in their mold design. And then we can contact him for more information, I guess.
David, I want to thank you for your presentation and for answering all of these questions. There were many more, and I will let everyone know that David will have a list of all of your questions available to him after this webinar ends, so he can get in touch with you and answer them more fully later on. For those listening who would like more information, obviously there is contact information for David on your screen. And remember, you can visit moldmakingtechnology.com for the archived webinars. I'd also like to thank the organizers for helping the webinar run smoothly, and to those of you listening, thank you for your time today. This concludes our webinar. Again, this is Cindy Kustash with Mold Making Technology, and I hope each of you has a great day.